In this video, I'm going to be looking at the work done by a variable force. We'll talk about the idea in general, but then we'll apply that idea to looking at the work done by a spring as we stretch it or compress it. So a variable force is one that changes depending upon a variable. A variable force is a non-constant force. For example, the drag force, the force of air resistance, is a variable force. It depends on the velocity. One of the versions, depending on the shape of the object, drag force for some objects is proportional to the speed squared. So the faster you're going, the larger the drag force is. And so it's not a constant force, but it changes depending on the speed of the object. Another force, and one that we're going to be looking at in this video, is going to be the spring force. And the spring force is proportional to how far you stretch or compress the spring. But again, both of these forces are forces that depend on variables. They depend on things that change. The forces are not constant. To understand how to find the work done by a non-constant force, we're first going to return to something that we've already looked at, which is the work done by a constant force. And so in this situation, we're going to look at a constant force of 10 newtons that's acting to the right, acting on a box that slides 15 meters to the right. And so we already know how to find the work done by that constant force. But we're going to look at this a little bit differently. If I were to graph the force versus position for this object, we have a constant force of 10 newtons acting over the full 15 meters. It's not a very interesting graph, but we have this horizontal line, a constant value of F, over that entire 15 meters. And we know that to find the work done in this case, it's the parallel component of the force, 10 newtons, times 15 meters, so the work done is 150 joules. Looking at this on the graph, we can see that this relates to the area between that graph of the force and the horizontal axis. We have the area of that rectangle. That rectangle has a height of 10 newtons and it has a width of 15 meters. And so the area between that graph and the horizontal axis is 150 joules. It's 10 newtons times 15 meters. And so the area between the graph of force and position is the work done. This is very similar to when we were looking at kinematics graphs. The area between the velocity versus time graph and the t-axis gave us the displacement, or the area between the acceleration versus time graph and the t-axis gave us the change in velocity of the object. This is another situation. We can look at the area, we can relate this work done to this area. So the area between the graph of F and position is the work done on the object. If we have a non-constant force, we could estimate the work done by that force by treating the force as being constant over small intervals and looking at the work done by that approximately constant force over each of those intervals. In calculus, you talk about Riemann sums. That's what this is. You're estimating this area by looking at the area of these little rectangular regions. And if we let those rectangular regions get thinner and thinner and thinner, we eventually get to the case where we're talking about the area between the graph and the horizontal axis. And so that area between the graph of F parallel and the horizontal axis gives the work that's done if we're graphing force versus position, or force versus distance. So for a force that varies, the work can be approximated by dividing the distance up into small pieces, treating the force as being approximately constant over each of those small pieces, finding the work done during each little piece and adding them up. Again, this is the Riemann sum idea, where you take all of these little pieces and you add them all together. This only gives us an estimate of the amount of work that's done. And so in calculus, you learn about going from Riemann sums to going to an integral. And so in the limit that the pieces become infinitesimally narrow, the work done is the area under the curve. So it's the integral from the starting position A to the ending position B of F parallel times dl. Here, F parallel is the force as a function of position, and here they're using the generic variable L for the position of the object. In the last slide we were using x, but it's force as a function of position integrated with respect to position. Again, this has to be force as a function of position, not force as a function of some other quantity. There are other situations. Sometimes we know force is a function of time. That's not this case. This has to be force as a function of position that we integrate with respect to position. Now we're going to focus specifically on the spring force. The force exerted by an ideal spring is given by Hooke's law. Hooke's law says that the spring force is proportional to how far you stretch or compress the spring. Not all springs obey Hooke's law. You have some springs, they're sometimes called non-Hookean. They don't obey Hooke's law, or sometimes they're called non-linear. As you stretch it, the force is not proportional to x. It might be proportional to x squared or x cubed, but many springs will obey Hooke's law, at least for a certain region. All springs, if you stretch them far enough, they stop acting like a spring and they start acting like a wire. But for an ideal spring, as we first start stretching it or compressing it, the force will be proportional to how far we stretch it. The way that we usually write it is the second version that's there, where the magnitude of that spring force equals k times x. K is called the spring constant, or sometimes it's called the force constant, and it describes the stiffness of the spring. It describes how difficult it is to stretch or compress the spring. The more force it takes to stretch at a certain distance, the bigger that spring constant K is. Something like a slinky that's very easy to stretch has a very, very small spring constant. Something like a garage door spring, which is very difficult to stretch even just a tiny little distance, has a much larger spring constant. Looking at that first version of Hooke's law, that's a vector equation that says that the spring force equals negative kx. And so what that's saying is that the spring force vector is in the opposite direction of x. That negative sign means that the direction of the force is back towards the unstretched position. So in the second diagram that shows the spring being stretched to the right, the spring force is back to the left towards its unstretched position. Or in the third case, where it shows that the spring is being compressed to the left, it shows that the spring force is to the right, back towards the unstretched position. So what we will often do is we will often use the second version of Hooke's law, that the absolute value of the spring force, or the magnitude of the spring force, equals k times x, and then just remember that the direction of the force is back towards the unstretched or uncompressed position. And in the equation, x is how far you stretch or compress the spring from its unstretched length. So x equals 0 is where the spring is not stretched or compressed, and x is how far we have stretched it or compressed it from that unstretched length. And so now we can look at the work done by a spring as it's stretched or compressed. The graph that's shown shows the spring force as a function of position. When x equals 0, when the spring is not stretched or compressed, the spring force is 0. And as you stretch the spring more and more, or you compress the spring more and more, as x gets bigger and bigger and bigger, the spring force gets bigger and bigger and bigger. F equals kx. We have this linear relationship, that the force is proportional to x. And so specifically looking at how much work is done by the spring as we go from 0 to x1. And so the force, when the spring is stretched a distance x1, the force is k times x1. The amount of work that's done is going to be the area between that graph and the horizontal axis. It's the area of that triangle. The area is 1/2 the base times the height. 1/2 times x1 times kx1. 1/2 the base times the height, which gives 1/2 k times x1 squared. To figure out whether that work is positive or negative, the easiest way to look at that is to look at, is the spring force in the same direction that the object was moving, which means that the spring does positive work on the object, or is the spring force against the motion of the object, which means that the spring force does negative work. But the amount of work that's done as the spring goes from 0 to x1 is 1/2 k times x1 squared. If we wanted to look at this in terms of calculus, work is the integral of f dx. It's f as a function of x dx. The force is kx, so it's the integral from 0 to x1 of kx dx. The integral of kx is 1/2 kx squared, And so we evaluate that from 0 to x1, which gives us 1/2 k times x1 squared. Again, that's the amount of work that's done by the spring. What if the spring was already stretched a certain distance x1, and we wanted to find how much work was done going just from x1 to x2? Graphically, the way we would look at that is we would look at the work done going from 0 to x2, which is 1/2 k times x2 squared. But then we subtract off how much work had already been done initially, 1/2 k times x1 squared. That gives us the area of this green trapezoid. So we had the whole triangle from 0 to x2, and we subtracted off the triangle from 0 to x1, and that left us with the trapezoidal region, which is that area from x1 to x2. So the work done going from x1 to x2 was 1/2 k x2 squared minus 1/2 k x1 squared. Again, in terms of calculus, we would look at the integral from x1 to x2 of kx dx. So the integral of kx is 1/2 kx squared. We evaluate that from x1 to x2, and that gives us our same relationship, that the work done equals 1/2 k x2 squared minus 1/2 k x1 squared. Again, this gives the amount of work done stretching or compressing the spring. We would still have to go through and identify, did that spring do positive work or did it do negative work, based on was the force in the same direction as the motion or was the force in the opposite direction of the motion. In a later video, we'll look at some applications of the work done by a spring as they're applied to solve certain problems.